Hi everyone, I'm going to cover 10.4, which is on the probability of disjoint and overlapping events. So first, let's make sure you know what a compound event is. We have actually talked about them, but it's good to clarify before we move forward. So overall, a compound event is when you're actually thinking about some combination of two events. Did A or B happen? Did A and B happen? So they go into a little more detail here. They say when you consider all the outcomes for either of two events A and B, you form the union of A and B. So this is the union here. You're including outcomes in A, outcomes in B, and you are including, just to be clear, the outcomes that are for both. Then, when you consider only the outcomes shared by both A and B, you form the intersection of A and B. So this is the intersection here. You're only considering outcomes that are shared or that satisfy both A and B. Here's another example of an intersection where they don't overlap, and we'll talk a little bit more about that on the next slide. But compound event is really like some combination of two or more events. Disjoint or mutually exclusive events. Disjoint and mutually exclusive mean the same thing, so those are the same. The thing that's different from those is overlapping. So, to find the probability of A or B, you must consider what outcomes, if any, are in the intersection of A and B. So these two are intersections. So you have to consider, are there any events that are shared? Two events are overlapping when they have one or more outcomes in common, as shown in the first two diagrams. So here there are some outcomes in common in this intersection, so they're overlapping. Two events are disjoint or mutually exclusive when they have no outcomes in common. So this would be an example of disjoint or mutually exclusive right here. The two events are not overlapping. Apologies for some of the background noise. Okay, so here are two formulas, probability of compound events. The second one only applies to disjoint events, and we're going to make a little bit more sense of why these formulas work when we encounter some examples. So I will continue throughout these slides to talk about why these formulas make sense. So if we're calculating the probability of A or B, it's equal to the probability of A added to the probability of B, and then you actually subtract out the probability of A and B. Okay, the intersection is what you subtract out. And the reason for this, we'll see, is that you don't want to end up counting outcomes twice. But that'll be easier to see in some of the examples later. Now, what I do think you can kind of understand right at this moment is if A and B are disjoint, that means there's no overlap. This formula simplifies to this one. Because if there's no overlap, there's no way that we can have an outcome that satisfies A and B. And so this probability would just be 0 if the events are disjoint. And that's why this last term goes away. And it's just the probability of A plus the probability of B for this, if they're disjoint. Okay, so what do disjoint events look like? Example 1 covers that. A card is randomly selected from a standard deck of 52 playing cards. What is the probability that it is a 10 or a face card. Now, these events, the event that it's a 10 and the event that it's a face card, are disjoint. The reason being, it can't be both a 10 and a face card. That's impossible. Either it's one of these 4 cards that's a 10, or it's one of these 12 cards that's a face card. Can't be both. So if we're asking what's the probability that it's a 10 or a face card, we add together the probability of A and B, and we don't have to worry about any sort of third term. 4 out of 52 is the probability that it's a 10 because there are 4 10s in the deck, and the deck contains 52 cards. 12 out of 52 is the probability that it's a face card because there are 12 face cards out of 52 total cards. Add those together, we get 16 out of 52, which simplifies to this. If you use a calculator, you see that the probability as a decimal is 0.308 about. Okay, now what do we do when there is some overlap, and meaning they are not disjoint? Card is randomly selected from a standard deck of 52 playing cards. So what is the probability that it is a face card or a spade? Okay, now, so the reason that they're overlapping is because there are some cards that are both face cards and spades. So there is some overlap here. So we would use this formula. We do have to subtract off that overlap at the end. There are 12 cards that are face cards. We learned that last time, out of 52 total. There are 13 cards that are spades, because a fourth of the deck is spades. But you don't want to count these cards twice. Like if you just add these together, you've added together 12 and then 13, but these 3 cards were in both groups. So in order to make sure you get the right probability, you have to actually subtract out those 3 so they don't get counted twice. Okay? You either have to consider them as part of just A or just B. So like you could do like 12 plus 10, because then you'd only be adding on the outcomes in B that you haven't already counted, and that gives you 22. And why do we know that it's 22? Well, if you just count up the number of cards that are inside A or B, it's 22. So you need to make sure that, whatever this formula gives us, that it's going to give us 22 out of 52, because that's how many cards are a face card or a spade. So just remember, when there is overlap, you need to subtract out that intersection to make sure you're not counting cards twice. Oh, sorry. So yeah, the final result, 22 out of 52, reduces to 11 out of 26. If you use your calculator, you can get a decimal of 0.423 approximately. Okay. Now, sometimes you might not be calculating the probability of A or B. That might be a quantity you have, and you need to find what the probability of A and B is. So here's an example like that. It says out of 200 students in a senior class, 113 are either varsity athletes or on the honor roll. There are 74 seniors who are varsity athletes and 51 seniors who are on the honor roll. What is the probability that a randomly selected senior is both a varsity athlete and on the honor roll? Okay, so you notice that hey, 74 plus 51, that's actually more than 113, which might initially seem weird until you remember, oh, well, there could be students who are varsity athletes and on the honor roll. And so adding these two together will not give you the total amount of students that are varsity athletes or on the honor roll. It'll be more than that. So, okay, we can use our formula. The events are overlapping, so we got to make sure that we include this minus the probability of A and B. Okay, what's the probability that someone in the senior class is an athlete or on the honor roll? Well, they told us 113 students out of 200 are varsity athletes or on the honor roll. Okay, so we plug that in for probability of A or B. What's the probability that they're varsity athletes? Well, 74 out of 200, because 74 out of 200 seniors are varsity athletes. What's the probability that they're on the honor roll? 51 out of 200, because there are 51 seniors who are on the honor roll. And we don't know what the probability is that they are both on, we don't know yet the probability that they're both on the honor roll and a varsity athlete. But we can solve for that. So like if we wanted to know, so they do some rearranging here basically. They add the probability of A and B on both sides, and they subtract 113 over 200 on both sides. And then we have that probability of A and B is like all this, 74 plus 51 minus 113. Sorry. Okay. Which is just 12. So it seems that there are 12 students who are both varsity athletes and on the honor roll, and so 12 out of 200 is the probability that that you pick a student that is both, and this is about 0.06. Okay. One last problem that kind of incorporates skills you've learned throughout this chapter so far. It says an American Diabetes Association, or the American Diabetes Association, estimates that 8.3% of people in the United States have diabetes. Suppose that a medical lab has developed a simple diagnostic test for diabetes that is 98% accurate for people who have the disease and 95% accurate for people who do not have the disease. The medical lab gives the test to a randomly selected person. What is the probability that the diagnosis is correct? Okay, so a tree like this can be super useful for lots of probability problems. And we're just kind of trying to map out all the different cases. So we pick someone from our population, and if we do that, so not thinking about the test yet, but if we pick a person, there's a probability of 0.083, in other words, 8.3% that they have diabetes, and then there's a 91.7% probability, or 0.917 probability that they do not have diabetes. Okay, and it's good to separate these out into these groups because the probability that the test is correct is different depending on the situation. So it's 98% accurate for someone with diabetes, and that meaning 2% inaccurate. But for a person who does not have diabetes, it's 95% accurate, meaning it's 5% like of the time it's not accurate. So then they ask, what is the probability that the diagnosis is correct? Well, there are two ways the diagnosis could be correct. One way is that the person has diabetes and it correctly diagnoses them as having it. The other is the person does not have diabetes and the test correctly diagnoses them as not having diabetes. So that's why I put my calculations next to those two cases. So what's the probability that a person has diabetes and gets a correct diagnosis? We multiply this probability times this probability to get this. That's one way we could get a correct test result. What's the other way? Well, it's that they don't have diabetes. The test also correctly says they don't have it. So I multiply these two probabilities, this one and this one. When I add those two probabilities together, I get 0.952, and that is, or in other words, 95.2%, and that's just the probability of a correct diagnosis through either of those routes that I outlined above. Okay, so map out all the cases, figure out which ones satisfy what they're asking. There were 2 out of 4 that satisfied it in this case. Calculate their probability, and then we added it together to find the probability that the diagnosis is correct. Okay, I hope that helps. Please email me if you have questions, as always, I don't know, you'll hear my voice next time I make a lesson for you. Bye everyone, have a good one.